Hello, my name is Eduardo and today I'm going to present the work entitled Optimal Allocation of Excitation and Measurement for Identification of Dynamic Networks. In this work, we analyze the problem of choosing the set of inputs and outputs in a dynamic network. Here is the outline of this talk. First, I will introduce the object of our study, dynamic networks. We will then discuss identifiability applied to dynamic networks. Based on these identifiability results, I will introduce the concept of excitation and measurement pattern. Then I will present the results obtained for two topologies, cycles and branches. Finally, I show conclusions we draw from this work at the end of this talk. Let us focus now on dynamic networks. In this work, we consider a dynamic network as seen in this graph. We adopt a modular representation from Van den Hoof et al. In this network, internal or node signals are represented by the letter W. A node signal is the sum of all signals entering a particular node. Between some node signals there are modules, which are represented by discrete time LTI systems. Each node may be subjected to a no excitation signal R that can be used as input of the network. The modules are collected in the network matrix G and represent the dynamics of the network. B represents a matrix that selects which inputs are applied in the network. The output I of the network is affected by measurement noise E, and only some node signals can be measured. Our objective is to estimate all modules in the best way possible from input-output data. In this work, we are interested in deciding which selection of input-output data would optimize a measure of the covariance matrix of the parameter estimates. We consider the following assumptions in our identification setup. The dynamic network is stable. We perform the identification task using the prediction error method and employ this optimal prediction model. Each input R is white noise with zero mean and variance sigma squared, and any input is uncorrelated for all other inputs. The measurement noise is independent Gaussian white noise process with zero mean and variance lambda, and is uncorrelated with all other measurement noise. The input and measurement noise are mutually independent. In order to perform a successful identification task, it is necessary that the modules are identifiable. We adopt the concept of generic identifiability from Bazzanella, Gavas, and Hendricks from CDC 2019 work. Generic identifiability is the ability to uniquely recover almost all the network matrix G compatible with the topology of the network from the input-output representation T. The input-output can be obtained by using the prediction error method, which is the method we adopt for the identification of the modules in the works. From previous works, we know that identifiability of the modules depends on the location of external excitation signals and measurements taken from the network. This translates to the questions of which nodes need to be excited and which nodes need to be measured. A key result is a necessary condition that asserts that for any network, every node must be either excited or measured. Once identifiability is determined, the next natural measure is the accuracy obtained by the identification method. Based on these results of generic identifiability, we introduce the concept of excitation and measurement pattern, EMP for short, of a network. Before introducing it, let us define the following sets. Calligraphical B stands for the set of excited nodes, while calligraphical C stands for the set of measured nodes. Now, an EMP is any combination of these two sets. Our interest is to obtain the most accurate experiment using the minimum number of excitation and measurements. For this purpose, we define the cardinality of an EMP as the sum of the cardinality of the excited and measured node sets. Not all EMPs guarantee identifiability of the modules in a network. We call a valid EMPs as those EMPs which render a network generically identifiable. We define minimum EMP as a valid EMP such that there is no other valid EMP with smaller cardinality. The smallest cardinality that any minimal EMP can have is the number of nodes in the network. The question of interest is to select the minimum EMP that provides the best accuracy for the parameter estimators. Our problem is therefore a problem of experiment design. How to choose the allocation of excitation signals and measurements so to minimize the measure of the covariance matrix. In other words, we would like to choose the minimum EMP that minimizes the trace of the corresponding covariance matrix. In this work, we focus on dynamic networks with two specific topologies. In the left, we see a dynamic network with a branch structure, while in the right, we have a cycle or loop topology. We are interested in deciding which minimum EMP is the best for these two topologies. In order to arrive at clear guidelines, we will assume that the following items hold. Each module has the structure of a gain multiplied by a single delay. We are going to use the asymptotic covariance matrix from prediction error methods. Now, we give two definitions that will be useful in this talk. A direct module is a module such that the node before it is excited and the node after it is measured. In all figures from now on, use the color green to represent that the particular node is being measured. Finally, a uniformly excited scenario is one such that all outputs have the same variance as sigma squared, and all nodes also have the same variance lambda. Let us look now to the results of cyclic networks. We start our analysis by looking at cyclic networks with only two nodes. We need to determine which EMPs are minimums for this topology. From identifiability results, we know that at least one node needs to be both excited and measured. Therefore, for a cycle with two nodes, there are 4 minimum EMPs to choose from. We have computed the analytical asymptotic covariance matrix for each minimum EMP and found the following analytical results. We first notice that under the uniformly excited scenario, the covariance matrix of EMPs 1 and 4 are equal, and the same holds for EMPs 2 and 3. We observe that the magnitude of the direct modules determines the most accurate EMP. That is, better overall accuracy is obtained when the largest module is a direct module of an EMP. Moreover, the direct modules are estimated more precisely in these EMPs than in the counterparts. If we additionally assume that the two modules are equal, all minimum EMPs produce the same trace of the covariance matrix. Finally, considering numerical results, we have observed that the difference between choosing the best EMP can be considerable with respect to the worst case, and in some scenarios even 4 times better. This will be observed for cycles with more nodes and also for branches. Now, for the 3 nodes case, the same identifiability result applies, which leads to 12 different minimum EMPs enumerated in this table. In the top right, you see an example of a minimum EMP for a 3-node cycle. We have computed the asymptotic covariance matrix of each EMP and observed the following. We simulated 1,000 of dynamic networks with random modules drawn from a uniform distribution under the uniformly excited scenario. The number of times each EMP was selected as the best is displayed in the bottom left histogram. Minimum EMPs from 1 to 6 were never selected as the best, while minimum EMPs from 7 to 12 provided the best results. What they have in common is that they have equal number of inputs and outputs. More specifically, minimum EMPs 7, 9, and 11 are likely to give the best results as they appeared almost twice than 80, 10, and 12. Once again, the magnitude of the direct modules played a key role in deciding the best EMP. One more time, we have observed a considerable gain in choosing the best EMP compared to the worst case, typically 24 times better in many experiments. We have observed similar results in a cycle network with 5 nodes. This principle remains valid. For the case of a cycle with 4 nodes, there are only 2 minimum EMPs. A minimum EMP is one where the even nodes are excited and the odd nodes are measured, and vice versa. Similarly to the 2 nodes case, we have observed analytically that when all factors are equal, the two minimum EMPs produce the same trace of the covariance matrix. We have tested numerically 10,000 networks and compared the two minimum EMPs using the analytical expressions for the covariance matrix. We have observed that the product of the directing modules is the key factor in deciding the best minimum EMPs. It worked in 99.64% out of the 10,000 simulations. Also, the gains in choose the best minimum EMP are once more considerable. The median was 8.7 and 20% of the numerical simulations were above 100. We now move to the network with branch topology. We start the analysis of branches with 3 nodes. For this class of dynamic networks, there is a corollary that states that the sink, which is the last node with no out neighbors, must be measured. The source must be excited, which is a node with no in neighbors. Finally, every node should be either excited or measured. Using this result, the case for a branch with 3 nodes have 2 minimum EMPs. We must decide either to excite node 2 or measure node 2. We have observed similar analytical results to the case of cycles with only 2 nodes. Under a uniformly excited scenario, the best minimum EMP is the one where the largest module is a direct module. The direct modules are estimated more precisely. When all factors are equal, both EMPs produce the same accuracy. For the case where the number of nodes is equal to 4, we have 4 minimum EMPs. Differently from the 3 nodes case, in this case there is only one minimum EMP that stands out. When all factors are equal, we have shown analytically that EMP2 is the one that provides the least variance. Even when everything is handily selected, from the 10,000 simulations, EMP2 is still dominant with 87.94% of the cases. A principle that emerged is that one should choose to excite the nodes near the source and measure the nodes near the sink. In other words, excite the first half and measure the remaining nodes as EMP2. We test this principle in larger branches, from 5 nodes up to 8. A numerical simulation of 10,000 dynamic networks were performed, and this table shows how often the 2 best minimum EMPs were selected. As we can see, those minimum EMPs that obey the principle of exciting the first half and measuring the rest are selected more often in the majority of the simulations. For an odd number of nodes, one needs to decide whether to measure or to excite the middle node, but both choices provide similar results. Now to the conclusions of this work. We have seen that directive modules play a key factor in deciding which EMP is the best. More specifically, one should choose the largest modules as directive modules. For cyclists, we have observed that directive modules are key factors in the selection of the best minimum EMPs. Moreover, minimum EMPs with equal shares of excitation and measurements tend to give the best results. For branches, we have seen that exciting the first nodes near to the source and measuring the last nodes near to the sink provide the most accurate results. Direct modules are important to give insight in which EMP is possibly the best choice, but they are not the only one determining factor for branches. For branches, we have results that indicate that those results presented here are valid even when the modules are rational transfer functions. A crucial aspect that we have observed for both topologies is the huge difference in the magnitude of the variance obtained by the best EMP compared to the worst EMP. Finally, we have seen that there is a considerable gain in the precision by choosing the best minimum EMP alone. In this work, we have explored the experimental design problem of selecting the set of inputs and outputs of a network such that the trace of the covariance matrix is minimized. I close my presentation here. Thank you.